Most of this course will deal with direct current circuits. Direct current, also called DC, is the type of current which is provided by batteries and solar cells, as well as the fuel cells for electric vehicles. It is this type of current which is output by the power supplies in computers, as well as cell phone chargers and other adapters commonly plugged into household circuits. The electric contact points of batteries are called the terminals. The positive terminal is called the cathode and the negative is the anode. When these battery terminals are connected with conducting wires to a load, such as a light bulb or an LED, electrons flow from the negative terminal through the load and return to the cathode. This setup, shown in the pictorial diagram at left, is a complete circuit. The electrons require a path to get back to the battery, or else there can be no electron flow. For historical reasons, originating with Benjamin Franklin, current flow is in the opposite direction to electron flow. Therefore, current flow is from positive to negative. In a circuit, the current flow is designated by the letter I, and it is measured in amperes. Remembering the directions of current flow and electron flow is essential when we deal with circuits involving electromagnetism. It is also critical in all electronic circuits involving semiconductors such as transistors, LEDs, or integrated circuits. The direction of current in a circuit is referred to as its polarity. For many components or devices, the polarity of the applied voltage is not important. For example, incandescent lights will operate in either polarity. Also, resistors or ceramic capacitors have no required polarity. But for components and circuits which do require adherence to the correct polarity, failing to do so will prevent the device from working properly and may result in damage to components or even cause a fire. In this slide, we have two illustrations of a simple electric circuit. The left one is a hand-drawn picture, and the right one is a schematic diagram using graphic symbols to represent the parts of the circuit. Clearly, the schematic diagram is much easier to draw. In this slide, we have three different methods of illustrating electronic circuits. The photograph on the left shows very clearly what the finished project looks like inside the metal enclosure, but we can see very little about the wiring involved. It shows nothing about the numerical values on the capacitors or which resistor is connected to another component. So it is of little help for understanding the circuit. The pictorial diagram in the center is very useful to tell us about the layout of the project. The wires are carefully drawn so we can see how to place them and how they connect to the chassis and the larger components. But the project included a printed circuit board with hidden connections, so the pictorial diagram is helpful but not sufficient to analyze the project entirely. The schematic diagram at right tells much more about the electrical aspects of the circuit. It shows all of the components and how they are connected together. It also may show the resistor values and the catalog part numbers for the other parts of the circuit. Sometimes a separate list of the components is also given. An electronic engineer would understand what the circuit does by just examining the schematic diagram and the component list. For the more complicated electric or electronic devices, showing both the pictorial and schematic diagrams make everything very clear. This next slide shows an illustration of a length of copper wire with a section magnified many times to show the individual copper atoms. In the center of each atom is its nucleus, which is surrounded by a number of electrons in their orbits. This is sometimes referred to as the electron cloud. The outer electrons in this cloud are the valence electrons, which, in conductors, are not tightly bound to their atoms. They are free to move from atom to atom under the influence of an electric field. These free electrons are what move through the conductor and constitute the electron flow. The individual electrons move very slowly, only about 0.8 meters per hour. That is at a real snail's pace. But because the Coulomb force is so strong, the electrons must keep moving and cannot jam up. The electrons leaving the anode of a battery push the electrons in front of them, and those electrons do the same to the electrons in front of them. The result is that the speed of electricity is very large, nearly the same as the speed of light. Next, we will consider how DC voltages add together. An example is when a flashlight uses 2 or more cells in combination to illuminate a lamp more brightly. When these cells are placed end to end, they are said to be in series with one another. In that case, the voltages are just added numerically, so 3 penlight cells will provide 4.5 volts. Sometimes voltaic cells will be connected in parallel, with all the anodes connected together and all the cathodes connected together as well. Then the common connections are applied to the load. In this case, the total voltage will be the same as the individual cells, but the capacity will be greater and the battery will last longer. Finally, cells may be connected in series and parallel at the same time. This is the case in electric vehicles. The voltage addition is the same as it is with a series connection. That is the sum of the inline voltages. And the total capacity of current is also greater, and the distance the electric vehicle will travel will be farther. This final slide explains the method of adding resistances together in series or parallel configurations. If 2 or more resistors are connected in series with each other, the total resistance along the path is simply the numerical sum of the individual resistors. In the example, RT equals R1 plus R2, which equals 22 plus 50, and that equals 72 ohms. When resistors are connected in parallel, the electrons now have more than one path to follow, and the combined resistance is less than the individual resistors. The method to use is to take the reciprocal of the sum of the reciprocals of the individual resistors. This works for any number of resistors taken in parallel. In the special case of just 2 resistors in parallel, there is a shortcut. The resistance of the pair is equal to the product of the individual resistances divided by the sum of the resistances. So in the case given in the slide, it would be RT equals R1 times R2 divided by R1 plus R2, which equals 22 times 50 divided by 22 plus 50, and that equals 15.278 ohms. This is called the product over sum method. But remember, it only works with just 2 resistors in parallel. The last case shows the resistors in series parallel. In this case, it is necessary to first calculate the resistance of the parallel pair and then add the last resistor in series. The last 3 slides show question sets which will help you to check what you have learned in this video.